Part 2, LHL and RHL. So in the previous class we understood what a limit is. A limit is like something which helps us understand what value a function is approaching as the input gets closer and closer to a certain number. So suppose our limit is x tends to a number, let's say for now, let's say 2, alright, and on the number line we have 0, 1, 2, 3, 4, 5, and on the other side -1, -2, -3, etc. Alright, and here is our number 2. So x can approach 2 from both sides. It can approach 2 from the left side and it can approach 2 from the right side, right? So we know 1.9 is less than 2. We know 2.1 is greater than 2. 1.999 is greater than 1.9 is greater than 1.9 but still less than 2. We know 2.0001 is less than 2.1 but is greater than 2. So what can we understand? We can understand that we can approach any number from both sides, from the left side and from the right side. So in the case of limits, there is LHL and RHL. LHL means left hand limit and RHL means right hand limit. So I'll read out the definition. The left hand limit of a function f of x as x approaches a number a is the value of f of x when x comes from values less than a. Okay, so suppose if we want x tends to 2, we can give x a number which is less than, if we are considering left hand limit, we can give x a number less than 2, which is probably 1.999. If we give this, we can say that x tends to 2 from the left hand. We can denote this by the minus sign. Minus would mean left hand side of the number. So x tends to 2 minus can be approximate to 1.9 or 1.98, any number very close to 2, which is on the left hand side of 2. Now for RHL, RHL means right hand limit. The right hand limit of a function f of x as x approaches a certain number a is the value of f of x when x comes from values greater than a. So in this case, we can approach 2 from the right hand side. So that means x can be a number very close to 2, which is on the right hand side. So we can say 2.0001, which is still greater than 2 but is very close to 2. So we can say x tends to 2 from the right hand side, which would mean positive. This is a superscript, so it's written on top right corner of a number. So 2 minus on the top would be LHL, 2 plus would be RHL. So in general, for a number a, we can denote LHL as limit x tends to a minus f of x for a left hand limit of that function, and for the right hand limit we can write limit x tends to a plus f of x. So these two necessarily don't have to be the same value if we are evaluating this f of x. Let's see how. We generalize limit as limit x tends to a f of x. Alright, but right today in this class we learnt LHL and RHL. So when does a limit of a function actually exist? So let's say if limit x tends to 2 for the function f of x. Let's give f of x a definition. F of x is equal to x plus 2. So here if we evaluate this, limit x tends to 2, x plus 2, which is equal to, giving x as 2, so 2 plus 2, which is equal to 4. So we get a definite answer. We can say that this limit does exist for this number and this function. Now what if we have a function f of x equal to 3x plus 1. This is a piecewise function when x is less than 2, and x square when x is greater than or equal to 2. Okay, this is our function, and suppose we find a limit. But in this piecewise functions we have to be very careful. Here we are limiting ourselves to 2, as 2 is the turning point of these numbers. So we need to find the LHL and the RHL limits of these two separately. So let's find that. Limit x tends to 2 minus for our LHL f of x. So what do we do? Limit x tends to 2 minus. Now we know our function has two outcomes, but which of these outcomes will we choose? We will choose the one which is to the left of 2, because this is LHL. So left of 2 would mean x is less than 2. So we choose this outcome. So we have to write this outcome, 3x plus 1. We can only have either one of these outcomes, and since it's LHL, we choose the one which condition x is less than 2. So we write 3x plus 1. Applying limit, apply 2 here. So 3 times 2 plus 1, which is equal to 7. Now for the RHL, limit x tends to 2 plus f of x, which is equal to limit x tends to 2 plus. Here we are approaching from the right side, so x is greater than or equal to 2, so we can choose x square. So our function's outcome would be x square. Applying this, we get 2 square, which is equal to 4. So in this case, you can see that LHL and RHL values are different. We evaluated them to be different values. So in this case, can we actually give a generalized expression for limit x tends to 2 f of x? Does this limit exist for this function? We have to say no, because when we are evaluating LHL and RHL, we get different values. So we cannot say that this limit exists for this function at x tends to 2. So with this problem, we can conclude a statement. The limit does not exist even if both one-sided limits exist individually, which would mean even though these two exist individually as LHL and RHL, they cannot be generalized as the limit of that function when x tends to that number. So we can say limit of a function exists only when LHL and RHL exist. That is, they are equal. LHL would equal to RHL. So limit will only exist when LHL and RHL exist and they are both equal. So for a limit to exist, we need LHL should be equal to RHL. In this case, they were not equal. So that would mean the limit of this function for x tends to 2 does not exist. Another example to actually solidify that concept in your mind. Let's give another function f of x equal to x square plus 1 when x is less than 2, and 3x minus 1 when x is greater than or equal to 2. Okay, this is a piecewise function, and we have to find if limit x tends to 2 of f of x actually exists or not. Question. So we have to find the LHL and RHL separately for a piecewise function. So let's write RHL and LHL, and let's evaluate. Limit x tends to 2 minus f of x would equal to limit x tends to 2 minus. 2 minus would mean x is less than 2. So we have to choose this outcome of the function. So x square plus 1, which is equal to 2 square plus 1, which is equal to 4 plus 1, which is 5. And for RHL, limit x tends to 2 plus f of x, which is equal to limit x tends to 2 plus, and since x is greater than or equal to 2 for RHL, we have to choose the second outcome, 3x minus 1, which is equal to 3 into 2 minus 1, 6 minus 1, which is also equal to 5. So when do we say a limit exists? A limit exists when LHL is equal to RHL. So in this case, both are 5. So that would mean since LHL and equal to RHL and both exist individually, limit of this function exists at x equal to 2. So yes, it does exist.